So now we're doing exercise 5.11, and here we're going to look at what happens when we have a time delay in our measurements and how that affects the stability of the closed loop system. So we're having the following case here. So we just have a system and then we have a time delay. You know that the Laplace transform of a time delay is an exponential raised to the power of minus s times the time delay. So capital T here represents the time delay we have in our measurements. And then we close the loop. We don't have any controller, just a closed loop. So this is equivalent to having a proportional controller with the value 1. And then we're going to see what happens with the closed loop system. And so the system G without poles in the right half plane has the Bode plot in figure 511b. So we have two different Bode plots here. They correspond to different systems G. So we have two different cases. Let's call this 1 and 2. And then we're going to determine for each of these cases for what values of the time delay t the closed loop system is stable. And one thing that is not marked out here in the plots, but that is quite important, is that the unit on the magnitude axis here is decibel. So let me just write that out. So this line here is 0 decibel. And in an absolute scale, 0 decibel is equal to 1. Alright, so if we look at the loop gain in this case, G O of S, the loop gain will just be the product between G of S and this exponential corresponding to the time delay. That will be G of S times e to the power of minus s times the time delay, capital T. So now we have to find out how this time delay will affect the Bode plots. So let's look at this loop gain in the frequency domain, G O of I omega, which is equal to G of I omega times e raised to the power of minus I omega, capital T. So let's first look at the magnitude. And once again, as you had in many previous exercises, the magnitude of a product is just a product of the magnitude of each factor. So this is the magnitude of G times the magnitude of E minus I omega T. This is a complex number written on polar form. So the magnitude is the factor that's in front of the exponential, and here it's just 1. So the magnitude of this one is 1, which means that the magnitude of G O I omega is equal to the magnitude of G. So the time delay is not affecting the magnitude curve. And that makes sense, right? Just intuitively. Even if we have a time delay between our measurements and our input signal, that shouldn't affect how the output signal is amplified. You should have the same relation there. So the magnitude curve is unchanged. The argument, on the other hand, we may guess that something will happen with that one. So the argument of a product is just the sum of the argument of each factor. And the argument of this exponential, once again, it's a complex number of polar form, so the argument is just minus omega t. So the argument curve is affected by this time delay, so we'll see a reduction in phase with omega t. So this also makes sense intuitively. If we have a time delay in our measurements, it's not very surprising that the phase difference between the output and the input signal is affected. So let's look at the cases that we have. Let's start with the first one. I'll take a new paper so we can see this. Okay, so case number 1. And what do we see here? Well, so 0 decibel was magnitude equal to 1 in an absolute scale. And the frequency at which the magnitude is equal to 1 is the crossover frequency. So we see that this is omega equal to 1 radian per second. That's our crossover frequency. And at that frequency we also see the phase margin here, the phase that we have left to minus 180 degrees. And we see that it's 40 degrees. So we have a phase margin of 40 degrees. And I'm going to transform this into radians since the angular frequency is radians per second, then it's much more convenient to work with. So 40 degrees is equal to 40 times 180 on pi radians, which is equal to 0.698 radians. And this was at the crossover frequency 1 radian per second. So obviously the phase can't be decreased with more than 40 degrees to avoid instability. So this phase decrease that we had, which was given by omega times capital T, must be less than 40 degrees, or 0.698 radians at the crossover frequency, to avoid instability, which means that this time delay, capital T, cannot be larger than 0.698 divided by the crossover frequency. And the crossover frequency was just equal to 1 radian per second, so this will be 0.698. So the conclusion is that the time delay must be smaller than 0.698 to avoid a unstable closed loop system. Okay, let's move on to task number 2, or case number 2. And this is in fact a bit trickier. It is hard to solve this problem just by looking at this Bode plot. So what we're going to do is that we're going to draw the Nyquist curve for this system. So let me make a plot here. So here we have the real axis and here we have the imaginary axis. And I'm also going to write or to sketch out the unit circle. Oops, not a perfect circle, but it doesn't matter. Can you see it? I'll move up. Maybe I can do like... Oh, we just go back and forth. Okay, then we're gonna mark out what we know. So let's start with this point. So at frequency omega equals 5, then we have a magnitude of 1, and we have a phase margin of 80 degrees. So the phase is minus 100 degrees at that frequency. So we have minus 90 here, so minus 100 is about here, and the magnitude was equal to 1, so that point lies on the unit circle. So this is the phase margin, 80 degrees. Oh, that was a bit unclear. 80 degrees. It's a little bit better. So this point corresponds to the frequency omega is equal to 5. And then the next point we have is the frequency omega is equal to 7. And at that point we also have magnitude equal to 1. So this is also on the unit circle. And here the phase margin is 40 degrees. So it's half as much as we have here. So that point is about here. Omega is equal to 7. So this angle here is 40 degrees. Like that. And then the next point we have is when omega is equal to 10. And then that point is also on the unit circle. But here we actually have a negative phase margin. And the phase margin is negative because we're on the wrong side of the real axis, so to speak. So that will be 40 degrees angle up here instead. So somewhere here maybe. That's 40 degrees there. And then we have that point there. Omega is equal to 10. So what is happening between these points then? Well, before we're coming to the first point, omega is equal to 5, the magnitude of this this system is larger than 1, and the phase is larger also than minus 100, which we had. So that would go, yeah, somewhere away here. Doesn't really matter exactly where. I think if you look at this, you'd probably find that it's doing something like this, I guess. The phase is quite low when this curve starts, and the magnitude is quite high, so something like that. And then between omega is equal to 5 and omega is equal to 7, the magnitude is in fact larger than 1. So the curve will be inside the unit circle. So very roughly, it would be something like that, right? So the magnitude here is smaller than 1. And then after this point, the magnitude goes up to 1.5, and it's equal to 1.5 at the same frequency where we have minus 180 degrees in phase. And that's when we intersect with the real axis. So let's mark that point out. Here is minus 1.5, so magnitude 1.5, and we're going through that point. So it's something like this. And then we're going back to the point omega is equal to 10. And after that, the phase is just getting lower and the magnitude is just getting lower. So I guess it will look something like this, and we will end up in the origin. So there's a lot of lines here. Let me just mark out this Nyquist curve with another color, so we're not getting confused. So I'm drawing it in red. Okay, like that roughly. So then we know that in order for the closed loop system to be stable, we need the point minus 1, which is here, not to be enclosed by this curve. And the way that can happen is if we make sure that minus 1 ends up in this region, so between the frequencies 5 and 7. So at the frequency omega is equal to 7, we have to decrease the phase of the system with at least 40 degrees, while at the same time, at the frequency omega is equal to 5, we cannot decrease the phase more than 80 degrees, because then the point minus 1 would end up over here, where we would have instability. So we have two different cases here. So the first one was at the frequency 7, so we could not, or we must have a phase decrease at frequency 7 with at least 40 degrees. So 7 times capital T must be larger than 40 degrees, which was 0.698 radians. And that means that capital T must be larger than 0.698 on 7, which is equal to 0.0997. And then we had the decrease at 5 radians per second, and that could not be larger than 80 degrees. So this one must, in other words, be smaller than 80 degrees, which is 2 times 40 degrees, which was this, So 2 times 0.698. And this implies that the time delay must be smaller than 2 times 0.698 on 5, which is equal to 0.279. So there are two requirements here. We must have a time delay that is larger than 0.0997 and smaller than 0.279. You can't see what I'm writing. Sorry for that. Okay, so yeah. It sounds a bit weird that you actually want a time delay in order to make the system stable. But if you have a system that looks like this, obviously that's the case. So this is the answer to exercise 5.11.